Hello, everyone. I'm Maarten Naesens. I'm a nephrologist at University Hospitals in Leuven, and I'm an EKITA board member since some 3 years. I'm very happy for the invitation today to be able to share with you some of the work we are doing in our group and to show this to the EKITA membership and all the people on our platform who are following this series. So I will now try to share my screen and go to the PowerPoint presentation I prepared for this meeting. Okay, so the topic I chose for this session is reclassification of kidney transplant rejection. So I will talk to you about some thinking tips on the pitfalls and solutions we have to overcome the definition of kidney transplant rejection. How can we reclassify this disease more as a spectrum of injury than as a presence or absence dichotomous classification? More a spectrum of injury rather than absence, presence of disease. So it is clear that the diagnosis of kidney transplant rejection is at the moment based on kidney transplant biopsies, and the international Banff classification is here used as the current ground truth. The Banff classification was initiated in 1991, is now more than 30 years old, and is still used with the same kind of background, which is the individual lesion scores that we can evaluate using histopathology in the kidney transplant biopsies. And you see here the individual lesion scores. You have glomerulitis, peritubular capillaritis, you have interstitial inflammation, tubulitis. All these different lesion scores are classified by pathologists semi-quantitatively from 0 to 3, and then indicate what type of rejection is present, antibody-mediated rejection versus T-cell-mediated rejection, as dispersed phenotypes of rejection after kidney transplantation. These individual lesion scores are then further classified not only according to the antibody-mediated versus T-cell-mediated origin of it, but also according to disease activity and chronicity, as you can see on this slide. What we have seen over the past 30 years is that the histological phenotyping of rejection has become quite complex, and sometimes we even call it Babylonian confusion, because there's many details in the current Banff classification that make it quite difficult for people to follow it accurately. Next to the difficulty and the complexity of the classification, there's another issue, and that is the fact that we try to dichotomize the histological picture, which is quite spectral with a lot of details from the 3-level or the 4-level lesion scores towards, again, as I said in the beginning, the presence or absence of disease. And it's clear that when you classify a given biopsy according to presence or absence of disease, this is not fully reflecting the large heterogeneity that we actually see within the biopsies, the spectrum of disease, injury, lesion score, severity that we see in these biopsies. So the dichotomization of the current classification of kidney transplant rejection is not fully reflecting the actual disease severity, but another problem is that this leads to a wobbliness of the classification on its own. And this is illustrated by a paper that Jasper Kallemijn from my team has recently published, where he compared kidney transplant biopsies classified according to different versions of the Banff classification for antibody-mediated rejection. And what he has seen is that the same biopsies as classified according to different updates of the Banff classification end up in different disease categories. For instance, in Banff 2001, there was a category of suspicious cases for ABMR that were only in Banff 2013 attributed to full ABMR, and these are the cases with C4D negative antibody-mediated rejection. Other cases were classified in Banff 2013 as suspicious for ABMR, but no longer classified as suspicious for ABMR in Banff in 2017. So the same biopsy that was classified as no rejection in Banff 2001 could have been classified as suspicious for rejection in Banff 2013 and no longer ABMR in Banff 2017. So really illustrating the wobbliness of the classification. Next to the fact that these thresholds that we use for classifying diseases are not definite, that they are not quantitative, it's also very well known that there are issues with the histological lesion scores on themselves, with sampling error, but also poor reproducibility of the histological scoring between pathologists, but also within pathologists. So the same pathologist sometimes gives different scores to the same histological picture. And then finally, the relation between the injury scores that we can see in the biopsy and the underlying etiology is not always clear. And so all of this together leads to issues with the use of the current Banff classification by light microscopy. We use it for daily routine clinical diagnosis of acute rejection, but it might be possible that in the future we overcome the problems with the Banff classification as gold standard. And in this presentation, I would like to go over some of these potential tools. So we might want to reclassify kidney transplant rejection not based on the iterative consensus-based scoring system, but by using mathematical reclassification of the histological lesion scores and the biopsies. We could also use a whole slide image analysis by computerized morphometry. And then also there's a lot to do about molecular microscopy, so using the molecular expression profiles of kidney transplant biopsies to reclassify rejection phenotypes. So I would like to start with the mathematical reclassification of kidney transplant rejection phenotypes. This is a study that was published last year by Thibault Vollet from my team, where he actually has used a training set of 3,500 biopsies performed at the university hospitals in Leuven, and then a validation set of 3,800 biopsies from Paris and Lyon in France. And using quite complex clustering approaches and also semi-supervised approaches, he came with the reclassification tool that was able to reclassify kidney transplant biopsies into 6 different clusters. Cluster 1, which is the cluster with absence of rejection, and cluster 2, that is DSA negative microvascular inflammation, cluster 3, that is T-cell mediated rejection cluster, cluster 4, that is a cluster of DSA positive cases, but that do not have the histology of antibody-mediated rejection, the cluster 5 that has the features of antibody-mediated rejection, and then a cluster 6 that is combining T-cell mediated rejection lesion scores with antibody-mediated rejection lesion scores. So the place on the polar plot on which each of the dots represents a single biopsy indicates in which cluster a given biopsy is located. But more interesting even is that this polar plot indicates on the x-axis or on the radius the sum of the weighted acute lesion scores, which is a weighted summation of the acute Banff lesion scores. And what is interesting is that Thibault could demonstrate that this weighted sum of the histological lesion scores, which we call the inflammation severity, was extremely nicely associated with the risk for graft failure after a kidney transplant biopsy. So really indicating that this polar plot and the clusterization algorithm that he built was not only able to classify different rejection phenotypes quite accurately, but also indicate some severity of kidney transplant rejection, which is currently completely lacking in the Banff classification. In a paper published in JASN 2021, we only focused on acute lesion scores, but we are now working on a new analysis where we also integrate chronicity in this algorithm, and where we show again that the higher the chronicity score of a given biopsy, the lower the survival is on the long term after the biopsy. And this is independent of the acute lesion scores. So again, some way to mathematically reclassify kidney transplant biopsies to hopefully one day be able to not only classify the cases according to the cluster or the actual diagnosis, but also on the severity of the rejection. This classification system or reclassification system is available currently in Python Anywhere platform, where people can log in and upload an Excel sheet with their Banff lesion scores and biopsy annotations, and then they get feedback on where a given biopsy is located on a polar plot. But more interestingly, you can also then download your own data, including the cluster, the theta angle of the polar plot, the radius of the polar plot indicating the severity. So really applying this tool to your own data. This is an illustration of a study that is ongoing by Elisabeth van Loon from my team, where she actually has been able to show that on a large set of biopsies and cases where she measured the urinary chemokines, that this urinary chemokine level associated very nicely with, again, the radius on the polar plot, the severity of inflammation, something that could not be done when you use rejection as presence or absence according to the Banff classification, where you of course see that the urinary chemokines are higher in rejection cases, but where you do not have the granularity to give a more continuous scoring and relate the chemokines to the spectrum of rejection severity. I do not have too much time, but I would like to go to the second topic of this presentation, where I would like to illustrate how we can use deep learning of kidney transplant whole slide images for diagnosis and reclassification of kidney transplant rejection. A nice example was published by the Paris group some years ago, where they have used multiplex immunofluorescence for different immune cells and kidney structural cells, where they then have applied automated analysis of the number of immune cells to have an idea of how the immune cell constitution actually associates with a different rejection phenotype. And I believe this is one of these studies clearly illustrating how image analysis could overcome some of the issues with the Banff classification, which is semi-quantitative, and actually use the percentage and the absolute numbers of graft infiltrating cells as measurable ground truths. A recent study to which we contributed as well by Jasper Kers and Roman Bullo from Amsterdam and Aachen has illustrated that you do not even need multiplex immunofluorescence images to calculate automatically presence or absence of rejection and rejection severities. What they have been able to show is that with the classic histological stains, PAS stains, H&E stains, Jones stains, that convolutional neural networks, so really deep learning algorithms, could lead to a very nice classification of the whole slide images purely based on computation, so not using information from the pathologist, and that this algorithm clearly is able to discriminate normal biopsies from abnormal biopsies, and even able to then further indicate which zones of the biopsies were used by the computer to indicate normality or indicate abnormality. Within the biopsies that show abnormal lesions, this algorithm is not yet sufficiently advanced to discriminate between rejection and, for instance, other phenotypes of injury. But this is clearly a way forward to overcome likely the burden of looking at many biopsies, and very likely to be in the future used as a addition to the normal light microscopy by pathologists and the evaluation of the histological lesions according to the Banff classification. So adding another layer and a robust layer of the rejection evaluation using whole slide image analysis. In the last few minutes of this presentation, I would like to discuss with you the place of molecular microscopy as a ground truth. So there is a lot of promise, and one of the pioneering centers in the world is the group of Phil Halloran in Canada, who has coined actually molecular microscopy for kidney transplant rejection. He has used over the past 2 decades Affymetrix gene chips, so microarray expression analysis of the whole genome to enable to reclassify cases according to the different types of rejection. Again, showing T-cell mediated rejection, antibody mediated rejection, mixed type of rejection, absence of rejection on types of plots I illustrated you previously, but without good idea of the severity of rejection, but still a quite powerful algorithm that enables you to discriminate the different types of rejection, not based on the morphology, histological evaluation, but based on the molecular expression of kidney transplant biopsies. Then we have tried to refine this further in our Leuven group, where Jasper Kallemijn again has looked at how many genes are actually needed to reclassify cases according to rejection. And while Phil Halloran is using whole genome transcriptomic analysis, Jasper was able to show that with only 4 different genes measured in kidney transplant biopsies, we have very good diagnostic accuracy for both antibody-mediated rejection and, on the other hand, T-cell-mediated rejection. What he also found is that these 4 genes not only enable us to discriminate between presence or absence of rejection, but also to see nice associations between the outcome after a given biopsy with a ROC area under the curve of above 0.80, which was also stable over time post-transplantation. And then Elisabeth has been able to show that using these molecular microscopical features, these 4 genes within kidney transplant biopsies correlated better with the expression of urinary chemokines of these same patients, illustrating again that the newer tools and the molecular microscopy could be more powerful in evaluating the severity of rejection than the current Banff classification, which is not primarily doing that. So this brings me to my last slide, where I think that with the current Banff classification, we are 30 years of having a very good system to classify rejection phenotype. This is a system that has worked, that is still working for our clinical routines. But one of the problems is that this classification is not the ground truth, and that the actual phenotype of rejection is something that is constantly refined, and we, with the research that is ongoing, discover more granular phenotypes of rejection. And with all the tools that we have, classic light microscopy, multiplex immunofluorescence, whole slide image analysis, molecular microscopy, we see different angles of the same phenotype, which we will never be able to grasp entirely. So the ground truth of presence or absence of rejection is something that we will never be able to catch completely. But what I think is that in the future, we will be able to compile the molecular microscopy with whole slide image analysis and with the classic light microscopy to have a much better view on how to classify the diseases and also how to have a better evaluation of the disease severity. So really going into accepting the concept of rejection as a spectrum of disease instead of absence or presence of a disease. And with that, I would like to thank you a lot for your interest in this presentation.